If you flip a coin, the coin will rotate multiple times before landing, but the question is, how many times? Welcome back to Engineered Bets. This is the first of a two-leg parlay, and it's your job to predict both of them correctly. The line for this first leg is 13.9 flips, which is slightly more than Gary V's average per garage sale. How was the line set? Well, the coin was launched from about a quarter of a meter off the ground, and by comparing its first and fifth frames, the coin had an initial linear velocity of about 1.5 meters per second, launched at an angle of about 105 degrees. We already know from the first episode how to split this up into components to solve for the time when a simple projectile will hit the ground using kinematics, which uses the potentially costly assumption that the motion is dictated by gravity alone. We actually don't care how much the coin moves to the left or the right, just how many times it flips, so instead of its horizontal movement, we'll look at the coin's angular movement. By roughly looking at the planes for each, the coin had an initial angular velocity of about 5,940 degrees per second, or 33 flips per second, where I'm defining a flip to be a 180 degree rotation from heads to tails and vice versa. Since it was also assumed there's no drag slowing the rotation either, there will be no angular acceleration, and just like before, we can solve this to see that if the coin is in the air for 0.42 seconds, it will flip 13.9 times before hitting the ground, and that's how the line was set. Pause now to predict how reality will vary from this simple model. And now it's time to see what actually happened. As you can see, the coin only flipped 13 times, meaning the under has hit. Congrats if you got it right, and now it's time to move on to the second leg. If you drop a bouncy ball off a ramp and onto a long counter, it will bounce multiple times before falling off, but the question is, how many times? Welcome back to Engineered Bets. The line for this second leg is 4.5 bounces, which is slightly more than Kawhi's game-winning shot versus the Sixers. How was the line set? Well, when a ball bounces, energy isn't perfectly conserved, so the velocity of the ball just before impact won't be the same as the velocity after the bounce. However, the ratio between these two velocities when colliding with the stationary surface is called the coefficient of restitution. To be able to easily measure this value, you need to cleverly manipulate this definition. First, square both sides and then multiply the top and bottom of the right-hand side by 1/2 the mass of the bouncy ball. That shows you that the square of the coefficient is the ratio of the kinetic energy of the ball after and before the impact. The kinetic energy of the ball just before the bounce is equivalent to the potential energy the ball had as it was released, assuming no losses during the fall. Likewise, the kinetic energy after the bounce will be converted to potential energy as the ball rebounds to its highest point. Substituting the equations for each of these potential energies and solving for the coefficient, you see that it's just the square root of the initial and rebound heights. Doing a test drop and measuring the before and after for 5 bounces, it was determined that the average coefficient of restitution for a bouncy ball on this counter was 0.94. With this information, it's time to quickly solve for the number of bounces using familiar techniques. For the ramp, we'll just assume energy is conserved, so the 0.067 meters of gravitational potential energy will be converted into kinetic energy, meaning the initial horizontal velocity of the bouncy ball for the next part will be 1.15 meters per second. Since we'll also assume no friction in addition to no drag, the bounces won't affect the horizontal speed, meaning there's no horizontal acceleration, and we can easily solve for the horizontal position, which looks like this. Since the length of the counter is 1.61 meters, we can see that the ball will travel for 1.4 seconds before it reaches the edge. Now we just need to see how many times it will bounce in this time. The ball will accelerate down from 0.22 meters above the counter until it reaches the ground 0.21 seconds later, which is the first bounce. Next, we take the vertical velocity at impact, which is negative 2.07 meters per second, and multiply by the negative of its coefficient of restitution to get its velocity after impact. Now we can repeat these steps, finding the time the ball will next bounce and verify that there's still enough room on the counter. Doing so, you can see that the ball should bounce a little more than 4 times before reaching the edge, so the line was rounded to 4.5 bounces, and that's how the line was set. As you pause to make your prediction, keep in mind that if you've ever played with a bouncy ball, you know just how bad some of these assumptions are, so as always, try to factor that or your intuition into your guess. Anyway, now it's time to see what actually happened. As you can see, the ball ended up hitting the counter 6 times, meaning the over has hit. Congrats to those who got both of them correct, and as always, let me know in the comments which specific factors you think contributed the most in both of these examples. Thanks for watching to the end, and I'll see you next time.